and the dual norm is Fresh differentiable, that itself the original Banach space is reflexive. This is quite strong property, but it's also Fresh differentiability for the unit ball in the dual is also the quite strong demand. So it's also a well-known fact from many years ago, discovered by cadets, that if we deal with a separable Banach space, and we know that this separable Banach space admits an equivalent Fresh differentiable norm, then the strong dual, I mean the dual of the space, is also separable. It's very classic stuff from many years ago. Now let's go to something which is originally discovered by Asplund, but of course he didn't use this name Asplund space. He called this space, which is going to be defined here, as strongly Fresh differentiable if this condition which is described here holds. But anyway, I'm going to call this Banach space Asplund just to be close to this notation we know today and is very useful. So a Banach space is called an Asplund space if every continuous convex function of that space is Fresh differentiable at each point of a dense G delta subset of E. By the property that the G delta means this is a countable intersection of open sets. So we know already what is this Asplund space, Asplund Banach space. And almost at the same time, but independently, Asplund and Lindenstrauss discovered that if a Banach space has, if a Banach space is of course separable and the dual is separable, yes, if the dual is separable, then this space is already Asplund space. So for Banach spaces with separable dual, the very easy information and very handy information says the following, that this space is already Asplund, so we have this connection with Fresh differentiability, which was already explained on the first slide. So we know what is the Fresh Banach space with the Asplund property. Okay, let's go to one step further. So I'm going to connect couple of, or to put together a couple of results. Let's first mention this very essential, very important paper of Deville, Godefroy, and Ziesler. And one should add Asplund, because Asplund already knew about this result. Also Namioka Phelps. So I didn't add this name, these two last names. I'm sorry. But we have already some very nice equivalent conditions, or I would say description of a Banach space to be Asplund. Okay, this is the first information, or just the beginning information. A Banach space is Asplund. This holds if and only if every separable Banach subspace of our space has separable dual, and the next one, every equivalent norm of the Banach space is Fresh differentiable at some point of this Banach space E. So we have three equivalent conditions for a Banach space to be Asplund. The second one is really very handy, yeah, because this says that if we have a separable Banach subspace of our original Banach space, so Asplund property forces our Banach subspace to have separable dual. So it's very easy to understand. I mean, at least the meaning of the item 2. So now let's go to a very special class of Banach spaces, namely Banach spaces of continuous functions, real continuous functions. And our our case at this moment is very also old result of Rudin, stating the following: if we have a compact Haldor space K, and we consider this Banach space of continuous functions. So if additionally we know that our compact space is scattered, I'm going to explain what does it mean. So K is scattered compact space, then the dual of the space has very concrete form, very concrete presentation, namely, this is just the Banach space of L1 over a compact with cardinality, exactly the cardinality of our guy K. So scatteredness, what does it mean to have a scattered property? So a topological space is called to be scattered if every non-empty subset A of X has an isolated point itself in the set A. So we have many examples of scatters, compact scatter spaces. I'm going to just to add one or two of them just to show what is the situation in our subject. But I need to mention next very important and crucial result of Namioka and Phelps. They simply characterize Banach spaces of continuous functions to be Asplund. In general, we know what does it mean. We have already this the picture from the previous slide, but for Banach space to continuous functions, situation is very clear. A compact space K is scattered if this Banach space CK is Asplund. So for scattered compact spaces K, we know that any Banach subspace of CK, any Banach separable subspace of CK has separable dual. Then we know that one should look about the consequences already mentioned in the Rudin result. So, for example, if we consider this compact segment 0 omega 1 of course this with this order topology, and is well known that this space is scattered. This space is scattered. Scattered property is inherited by any subset. And by the way, any topological space which is scattered is also a bare space, means that intersection of any countable family of dense open sets is dense. This is a equivalent one of equivalent descriptions of the topological space to be bare. So now another result of that time, but now we have another two different essential and very distinguished specialists, Jane and Rogers, and Rybarska is another person was always responsible for this result I'm going to mention now. So now we are going back to this general case when E is a Banach space, but description of characterization is presented in some different way. We have a Banach space E, we have a dual with the unit ball. Let's consider this dual with the weak star topology. So it turns out that our Banach space is Asplund if and only if this object is fragmented by the metric generated by dual norm. What does it mean? Will be mentioned here. Right, next slide. So just to recall this concept already introduced by Jane and Rogers, but the main idea or the main task was related with a theory of renorming. So they used already this concept to study some problems for renorming theory. But at this moment, I'm going to just recall to connect this story with Asplund property. So if X is a topological space, and we have on this topological space some metric, we used to say that X is fragmented by this metric. So this topological space is fragmented by this metric, if for every epsilon greater than 0 and every non-empty subset M from X, there exists an open set, of course, with must be non-empty because of this next step here, set we let's call D, such that this intersection is non-empty, and diameter with respect to this metric rho is less than epsilon. So this is the definition due to Jane and Rogers. So Asplund property for Banach space could be described by using special metric approach or metric geometry related with the unit ball. Of course, this unit ball in the weak star topology is compact space, compact Haldorf space, and we need to know something about this fragmentability of this ball with respect to this metric. Metric is just the dual norm of our Banach space. Okay, so now if the main idea or the main topic of my talk is related with the question which is going to announce here, characterize spaces of continuous functions on a Tikhonov space. So this is most general situation when this space is endowed with a compact open topology. Compact open topology. So the question is, when this space, or better, characterize this space as being an Asplund space by a suitable property of a Tikhonov space X. So simple, in other words, we would like to know what does it mean, or how to characterize X to have CKX Asplund. So by the way, we shall say that this space of continuous function with compact open topology is Asplund if every separable Banach subspace of this space is separable dual. So you can imagine we have exactly the same task. I mean, the property which originally was discovered by or described by Namioka Phelps, this property is kept up here, but we just want to get possible larger class of spaces of that time, not necessarily compact spaces X, but for larger class of spaces for which the same conclusion holds for this space. Yeah. Okay, so now this is the main section of my talk. So Asplund spaces over Tikhonov space. Asplund spaces CKX over Tikhonov spaces X. So first, something what I like to mention here is just very fresh, very recently obtained result related with fragmentability. This result is due to Komisarczyk and Megershvili from the Tel Aviv University. And they called a locally convex space to have Namioka Phelps property. These two names we had already in previous slides. So the space locally convex space has Namioka Phelps property if every bounded set in this locally convex space is fragmented on each weakly star compact equicontinuous subset of is fragmented on each weak star compact equicontinuous subset called K in this case of the dual. So what does it mean? The definition is very simple. The definition is related also with fragmentability. This case means the following: for each non-empty subset A of the compact guy K, and each epsilon greater than 0, there exists a weak star open subset in the dual. So we have in the dual weak star topology. So there exists such subset for which the intersection is non-empty, but and diameter of such here distances when x is running over this intersection and b is running over this bounded set is less than epsilon. So why I'm going to mention this result? Because here we have this result of both Komisarczyk and Megarashvili, and they got something already, which especially refers to first condition, which first item here. So for Tikhonov space X, the following assertions are equivalent. X is, we used to call in topology K-scattered, means that every compact subset of X is scattered. Every compact subset of X is scattered, not necessary. The whole space is scattered, not necessary. So the CKX Znamioka-Fels property is somehow related with spaces, Banach space with Znamioka-Fels property. And we have something which is maybe not interesting at this moment because this is more or less connected with dynamic systems or dynamics of spaces of continuous function. Both guys are working on dynamic systems, and this item 3 they used to get or to solve some questions related with dynamic systems. Okay, so the problem or the general task for the work is to characterize Asplund spaces for this space in continuous functions for Tikhonov spaces X with what I mentioned here, paying additional attention to some interesting special cases where in principle X is not compact, because this compact, when X is compact, the problem has been already solved by Namioka and Fels, but for more general and very natural cases, spaces, I would say here pseudo-compactness or even omega boundedness. Surely I'm going to recall these definitions of two objects. And let's recall that a topological space is omega bounded if every countable subset of X is relatively compact. So if we know already, these implications are trivial. So omega boundedness trivial implies countable compactness. This property implies pseudo-compactness. Just to recall what does it mean to pseudo-compact space. A topological space is pseudo-compact if X is pseudo-compact if every continuous real function of X is bounded. A real continuous function is bounded. So if you take any continuous function, this image should be located in some bounded or some compact subset of reals. So there is some more general concept which is very useful in function analysis of spaces with continuous functions. Omega boundedness implies something which is called Warner boundedness. The description of this last property is provided here. That means for each sequence of pairwise disjoint open sets, one should get a compact K from X, for which the number of these natural numbers for which this intersection is not empty is infinite. It's a little bit technical, but this the consequence of this definition is very useful. It means that the space of continuous functions with compact open topology admits a fundamental sequence of bounded sets exactly when X is Warner bounded. Fundamental sequence bounded sets means we have a sequence of bounded subsets, topologically bounded subset of this space, covering our space with extra property that any bounded set from here is located in one number of the sequence, which is in case. And there's another information, omega boundedness implies really omega Werner boundedness. The converse fails. This is a very, very natural example showing that two concepts are not equivalent. Maybe I need to mention something that omega boundedness, when X is k-scattered, for example, when X is itself scattered, this X omega boundedness of the space is equivalent to some property, which is nice generalization of Grothendieck capital DF property. This is little df property introduced by Yarkov a long time ago, but it's nice object for investigation if we want to study topological analytic properties of spaces for continuous functions. Okay, this is some kind of preparation. Now, the characterization we obtained in our drawing work, drawing project, Leiderman from the University of Beersheba, Israel, Kurek from the Czech Academy of Science in Prague, and we proved the following. You can see here, X is just omega bounded or Czech complete. So with Czech completeness, we know surely what does it mean. Omega boundedness I already defined. These two concepts are independent in such a way that you can have a omega bounded space which is not Czech complete and Czech complete space which is not omega bounded. But for these two classes of spaces, either omega bounded or Czech complete, we have equivalent conditions. X is scattered. X is k-scattered, so that means here any compact subset of X is scattered. So if we are working in classes, in classes like here, k-scatteredness for such spaces implies scatteredness. So it was already well known that for Czech completeness, for Czech completeness, X is scattered if and only if any compact subset is scattered. So we have another class of spaces for which exactly the same situation appears. And it's something magic information. Item 3, we don't know what does it mean. I'm going to explain later. And we have another, this is just the problem we are going to connect, scatteredness and Asplund is, you can see we have two equivalent conditions and our object is not necessarily compact. So we have exactly the same conclusion like by Namioka Phelps, but this much larger class of spaces for which these two conditions, I mean item 1 and item 4, are equivalent. So you can see here in a couple of minutes, still have time, that this property of X is delta 1 space is also very crucial. So, so now we are talking about delta 1 without adding at this moment the definition, but we can see the following. X, if X is, for example, this is just conclusion here, if X is Czech complete space, then X is scattered if and only if X has this property deal or is delta 1 space. Still we don't know what does it mean, but this corollary is much more concrete. So if X is compact, we know already that X is scattered if and only if this Banach space is Asplund, but this property which is going to define is also described by the Asplund property. So if you are working, at least if we are just trying to understand the property of X, for compact X, delta 1 property is equivalent with scatteredness. Okay, so I need to mention that already Kurka 1 or 2 years ago proved, without using this phrase delta 1 space, that the compact space of the Banach space, for compact space X, this Banach space Cx is Asplund if and only if X is a delta one space. He didn't use this notation, but he just used some, in fact, definition of delta one is going to be explained in 2 minutes. So what I already mentioned, Asplund proper, the check completeness and omega boundedness are independent concepts. So the theorem 7 is just split it into 2 parts. The conclusion is exactly the same for both concepts. So one should mention that the theorem, this assumption I already provided, omega boundedness cannot be removed. It's a long paper, long time ago. Juhász and Van Miel constructed a countable compact space which is not scattered, is located as a dense subset of this difference beta omega minus omega, with all countable subsets scattered. So a very easy procedure shows that this X is k-scattered. So we have a k-scattered space, is not scattered. Our starting space X is not omega bounded, so at least we know already is nothing mentioned about here delta one property, but at least it is clear here that if we drop this assumption about omega boundedness, something is collapsing in our theory. Okay, so now maybe I skipped this example 10. But you see, I already mentioned that omega boundedness implies Warner boundedness. So one might be tempted to try to prove this or to get this theorem 7 even for the larger class of spaces X, namely Warner boundedness. But quite recently, my colleague from Warsaw sent me this example. It's quite long example, so I don't have time to look at this to show it. But anyway, it says that one can find a Warner bounded set X, which is not omega bounded. So we have a more general situation, and for which every compact subset is scattered, but itself this space is not scattered. So this is another information that in some sense, this assumption we have for theorem 7 are optimal, what I present. Okay, so now delta spaces and delta one spaces. Okay, so let's start with definition. It's just, I need to add here, this already concept of delta set was reals was already provided by Reed and Van Douwen. So what is the situation? We have a topological space X. It's called delta space, respectively delta 1, if for every decreasing sequence, for this case, countable subsets for delta, when we deal with delta 1 space, with empty intersection, we can get a sequence of open subsets of X in such a way that any Dn is located in Dm, but still this intersection is empty. So delta space property, which appeared here in this definition, in the past was studied by Reed and Van Douwen and many people, other people, but in reals. So we had some very strong obstacle, I mean meterizability and separability. So working in separable spaces, delta set appears in the reals with some mysterious conditions or mysterious properties. So very familiar and very connected objects, almost studied in the reals, are presented here as strictly connected with delta sets. A Q set, this is a set on the reals with the property that any subset of X is G delta. A lambda set, this is a set with the extra property that each countable subset of X is G delta in X. So we have this chain of implications, and already Kuratowski constructed uncountable lambda set in ZFC. So this means, if you look at definitions that uncountable, separable metrizable delta one spaces exist in ZFC. Situation with delta sets is totally different. It's already a result of Hausdorff. You can imagine how long ago this property has been discovered. So if X is uncountable Q set with cardinality essentially less than continuum, if X is uncountable delta sets, then the cardinality of X is essentially less than continuum. So that means under CH, continuum hypothesis, we don't have uncountable Q sets. This was a result of Hausdorff. And another set theoretical assumption here, Martin axiom and negation of CH, if X is a subset of reals with cardinality less than continuum, then this set is already the Q set. This is some result of Martin Solovey and Mary Rudin from 70s. Okay, another result of that type, we are still working working in reals. So no delta set in reals has cardinality C. There was some improvement on the previous slide from 77 discovered by Przymusiński. Our definition, which was provided on the previous slide, we decided to jump out from reals to topological spaces, in principle to topological spaces, so we could have more space to investigate. And what we proved already, any metrizable scattered space is delta one. But still the question about what the situation with metrizable, uncountable, separable delta spaces is under some conditions related with axioms, with set-theoretic axiom. For delta one spaces, the situation what I mentioned already here is totally different. Uncountable, separable, metrizable delta one spaces really exist in ZFC. So it is quite handy object for investigation. Definition is very similar, yes, but we are just working with countable sequence of countable sets, not necessarily uncountable. So what next? Compact delta spaces are scattered. So for example, 0 omega 1, which was already mentioned before, is not a delta space. It's not a delta space. But for very concrete objects, well recognized in topology and function analysis, I mean compact abelian spaces, we know that this guy is a delta space if and only if X is scattered. So we have a nice class of topological spaces which are delta spaces and at least compact abelian spaces. So delta sets, I mean, you are coming back to reals. What I mentioned here, what is written here, has been used in the study of two central constructions in topology, general topology, Moore-Nemitsky plane and the Pixley-Roy topology. So for example, if Mx is subspace of this Moore-Nemitsky plane, which is obtained by using only a subset X of the x-axis, Reed proved that this space is countably paracompact if and only if X is a delta set. So this is still the question about how to get it, concrete examples of delta sets in reals, and it's showed here that we need to add some set theoretical assumptions. What I mentioned already, that delta one spaces are much easier to investigate because we don't need any additional concept from a set theory. Okay, so now I'm going to complete my talk with two extra examples, which are connected with delta spaces and delta one spaces. So this is Tikhonov Planck. This is nice object, which is just the product of these two guys, and 2 points are removed. So it's well-known fact that this is separable, is not omega bounded. Maybe less evident that this space is Warner bounded. So it's Warner bounded, but it's not omega bounded. It's of course scattered. It's not delta space, but it's delta one space. There is some distinguished situation between delta one spaces and delta spaces. And another very interesting is also well recognized and investigated by many people, so-called space in Izbel-Mrówka space. So the starting point is just to consider maximal almost disjoint so-called MAD family in the natural numbers. So with special topology, I'm not going to define this topology. This space in this Izbel-Mrówka topology space, in the Mrówka space is just a pseudo-compact space, which is separable, is scattered, is not countable compact, so therefore is not omega bounded. But if we take one point, is 1 point, in fact, this space is locally compact. So if we take 1 point compactification of this guy, we'll get a delta space. So the 1 point compactification of the space is a delta space, which is scattered, but it's not Eberlein compact. So this shows that if this shows that we can get the delta compact delta spaces even scattered not being Eberlein compact. So I guess my time is over. I'm almost on time.